Okay, everybody. So apologies. There's something went wrong. Something went wrong with the PowerPoint presentation on this machine. We've had to correct. Okay, so I'm going to summarize some of the results on cosmological parameters from Planck. There's been very little discussion so far, so I want to see if I can generate some more audience participation. And so to do that, I'll say a few outrageous things. Okay? So first, my history of CMB research is summarized in this view graph. And you see that I've made room for further evolution. So hopefully there'll be some further evolution. Next thing is these are the 9 maps from Planck that you've seen. So I'm showing this so that everybody is absolutely clear that this picture that's on the front of your books and so on gives you completely the wrong picture of Planck. You do not peel back lots of galactic emission, dust emission in the case of this picture, to reveal the CMB. The CMB is beautifully visible outside the galactic plane at the main CMB frequencies of 70, 100, 143, and even at 217 at high galactic latitudes, it's pristine CMB. And as a result, in the high multipole likelihood, we do no component separation at all. We deal with galactic emission by masking the sky and by modeling unresolved foreground emission. So this is the power spectrum. So as Simon described, the likelihood is constructed as a hybrid. So 87% of the sky using a component separated map at low resolution via a Blackwell-Rao estimator gives us the likelihood at low multipoles. That's up to L of 49. That's shown by this dotted line here. So this is a logarithmic scale here. And then the high L likelihood shown on a linear scale. It's composed, in this case, by selectively masking the sky at 100, 143, and 217. And all of the cross spectra at those frequencies. So a few points about this. The first is that this red line is the best fitting 6-parameter lambda CDM cosmology. So I'll call that the base LCDM cosmology. And it provides an extremely good fit to the data, except at low multipoles, which I'll come back to at the end. So one of the things about Planck is that with this level of precision, the conventional power spectrum plots are really uninformative. There are error bars on these points, which you can't see any longer. The individual grey points here are the power spectrum multipole by multipole. So it's much more informative to look at residual plots of residuals with respect to the best fitting theoretical model, and then you can start to see interesting structure. The second thing is that, again, as Simon described, we have to solve for unresolved foreground components which are not negligible at high multipoles. So in addition to diffuse galactic emission at low multipoles, we have to deal with point sources, with cosmic infrared background, and other unresolved components. And we do that by solving for parameters describing those unresolved foregrounds at the same time that we fit for the cosmological parameters. So there is no unique power spectrum from Planck. What you have here is a maximum likelihood solution combining the frequencies that are used at the high multipoles with a foreground model, the parameters of a foreground model determined from a likelihood analysis including the cosmological parameters. Okay, so these are the residuals. And this green line here shows you the error model that we compute that describes the distribution of the individual L by L points. And this model also accounts for all of the correlations between different multipoles. So this illustrates, so this shows the Planck spectra now without foreground subtraction. So this is actually what we measure. Okay, so you can see the best fitting cosmology, and then at 100 gigahertz, 143, 217, the relative importance of the foregrounds that you have to model and subtract to high accuracy. Now, the foreground model that we've adopted, it also includes a lot of other nuisance parameters like relative calibration coefficients between different frequencies and beam uncertainties and so on. So there are a lot of parameters in addition to the cosmological parameters to solve for. When we use Planck on its own, we use relatively broad priors on the foreground parameters. For the base cosmology, base LCDM model, that's absolutely fine. There's very little sensitivity to those prior ranges. But when you start to look at more extended models, then you have to be more careful about modeling the unresolved foregrounds. As a basic rule of thumb, if you read these papers, if you see a difference in looking at extensions to the base cosmology, if you see difference to the cosmological parameters between using Planck with broad priors on the foreground parameters and then using Planck in combination with high multipole C and B experiments, then you should be suspicious that there's a potential foreground sensitivity to those models. So what we use normally as indicative of our best parameters for cosmological analysis is combining Planck with power spectrum measurements from SPT and ACT that have higher angular resolution and extend up to multiples of nearly 10,000. And so we're using the high L experiments in effect as additional information to constrain the unresolved foreground parameters. In addition, again, as Simon said, we're not using Planck polarization at low multipoles, so we're using WMAP polarization at low multipoles, and that's what we use to constrain tau. So in the jargon of the paper, best CMB parameters come from a combination of Planck plus WMAP polarization plus high L experiments. Okay, so this shows a little bit more on consistency. So at 143, the 143 cross 143 spectra, we have 3 unpolarized maps and 2 polarized maps. So we have 5 maps that we can cross-correlate. So that gives us 10 cross spectra, and these are the 10 cross spectra on top of each other. This is the deviation around the mean, so the root mean square deviation around the mean. And the red line here is just joining the dots. So that's the RMS scatter of a single measurement. And this is 0.2% of the red line. And so you can see these spectra are consistent with each other to better than 0.2% at multiples less than 1,000, and then become noise-dominated at high multiples. That's the equivalent for 217 cross 217. Here we've got 4 temperature maps, 2 maps with polarization, So there are 15 independent cross spectra. And again, it just shows remarkable consistency. This is the temperature power spectrum on an expanded scale. Again, compared, so the lower panel shows the residuals with respect to the best fit base LCDM cosmology. So where we have residuals like this, these are all as expected given our covariance matrices. So there's nothing unusual here. Whoops. You'll see a dip here. Okay, as far as any tests that I've done, this dip is consistent with our expectations from instrument noise and the correlations induced by the foreground model. But you will see, for example, if you go into the inflation paper, you will see a test of reconstructing the power spectrum, which responds to this dip, and that paper has a tentative claim for about 3.1 sigma deviation or detection of a feature at a wave number of 0.1 inverse megaparsecs. So whether that is a consequence of the statistic itself that's been used to make that reconstruction of the power spectrum, or whether it's some low-level systematic in the data that we don't have any candidate that could produce an effect like that. We don't know at the moment. Then these are the TE. This is the TE spectrum. And as Matthew and Simon said, the red line here is not a fit to these data points. It's computed from the best fit model to the TT spectrum. The important point here is that, and that's the EE, the important point here is, and the scientific point that we can demonstrate with this, is that here there's no correction at all for unresolved foregrounds. Okay, so whereas unresolved foregrounds are important at high multipoles in TT, they've been completely neglected here. And so that gives us added confidence that the parameters of the underlying cosmology, the best fit cosmology, are not far wrong. Okay, so this is the power spectrum of the lensing deflection field. So that's an additional power spectrum constructed from Planck, and so you'll hear more detailed discussions of this and how it was computed. So that's shown by the red points. And then the black line and the grey band are what we expect from the best fit parameters to the base LCDM cosmology. And these are the residuals. So it provides a very good fit to the lensing spectrum. Okay, so now going on to other astrophysical data. So what I'm going to do is quickly run through, the base LCDM cosmology fits the TT spectrum from Planck extremely well. So what I'm going to do is just quickly run through some additional data, astrophysical data, and ask the question of does that cosmology fit the other astrophysical data. So this shows results from baryon acoustic oscillation surveys. So RS is the sound horizon at the time that baryonic drag becomes unimportant, and then dV is a combination of angular diameter distance and the Hubble parameter at the effective redshift of the survey. So what these experiments measure, so that relates this to a physical scale on the sky. Whoops. So that's what the baryon acoustic oscillation surveys measure. And then that's divided by the predicted number for the Planck cosmology with plus or minus 1 sigma band. And you can see that it provides an absolutely brilliant match to the measurements. These two measurements are the most accurate measurements, and these, so this one is based on an analysis of the SDSS DR7 galaxies, and this one of the first BOSS data release. And in both of these cases, the groups have made a correction for redshift space distortions, and that allows them to measure the baryon acoustic oscillation features with higher accuracy. So everything is compatible. Now you can immediately infer from this that if we look at curved models with curvature, or models with varying W, the solutions will lock on to a spatially flat universe and solutions with W equals -1. Okay. Now, this is interesting because in the base cosmology, the Planck value of the Hubble constant is 67.3 plus or minus 1.2. And that is discrepant with direct measurements. So it's compatible with WMAP 9, but with a smaller error. And it's discrepant with direct determinations of the Hubble parameter using traditional Cepheid calibrators to the distance scale. So these three techniques, this is the old HST key project. These are all compatible with each other and discrepant with Planck. So this discrepancy is around 2.5 sigma. Okay, so it's a borderline significant discrepancy. Okay, now what this tells you is that if you start combining the CMB data with these direct measurements, you will find 2.5 sigma pulls to new physics. Okay, so it's often said that that WMAP initiated a new era of concordance cosmology, and I wanted to get a phrase into this paper saying that Planck has introduced a new era of discordant cosmology, but my collaborators wouldn't buy that. But the point is that Planck is a very precise data set. And with precision, with that level of precision, if you start combining with other data that has systematics, you will get wrong answers. You will get pulled towards new physics. So you have to be aware of that and be more sophisticated about how you handle data. Just don't take all of the data as black boxes and combine. That will potentially give you erroneous answers. Okay, now that's direct measurements of H0. There are also geometrical measurements. This is a megamaser distance measurement to this galaxy UGC 3789. So this measurement here uses NGC 4258 as a megamaser first rung calibrator. But this galaxy is more distant, and so it's outside of the immediate vicinity of the Hubble flow, and you can use it to give you a direct determination of H0. This is a gravitational time delay measurement, and then this is an old measurement of using Sunyaev-Zeldovich plus X-ray measurements to get a distance scale from rich clusters of galaxies. Okay, so all of these numbers seem high compared to this number. These two in particular are geometrical measurements. So that's potentially worrying. The discrepancy between Planck and the time delay measurement is also 2.5 sigma. Now, I had a correspondence, since the papers appeared with Jim Bratz from the Megamaser project, who said this is out of date. So there are more new measurements on UGC 3789, and there's a second distant megamaser. And H0 has now gone down. So that's where the new measurements sit. Okay, so this is a paper in proof that Jim said I could use the results from. And the new measurement is 68 plus or minus 4. So this will go into a revised version of our paper. So it's an interesting discrepancy, but be aware, if you literally believe these measurements, you are going to be forced in the direction of new physics if you combine with Planck. So to continue making enemies amongst the rest of the astronomical community, I'll tell you what happened when we looked at supernovae. So this is the SNLS compilation. So it uses the Supernova Legacy Survey objects, supernovae at intermediate redshifts combined with SDSS supernovae, local supernovae, and HST supernovae at high distances. With a really, what I thought was an extremely thorough analysis of potential sources of systematic error and construction of a covariance matrix, and very selective use of data, no historical data here. This is the Union 2.1 compilation, which uses historical data, so you can see that the scatter is just much larger in this compilation. This is the plus or minus 2 sigma band from the Planck cosmology. And you can see that it lies low compared to the SNLS sample. It's pretty compatible with the Union 2.1 sample. So that was not what I was expecting before we did this, because this should be the cleaner sample. This shows posteriors for omega matter. So in the base cosmology, then we can use this to constrain omega matter, or equivalently omega lambda. And this is the Planck posterior. And so again, you see with the SNLS sample, it's discrepant at almost the 2 sigma level. The Union 2 sample is shown by this black dotted line. Posterior, that's okay. And then if we separate out using different light curve fitters, analyze the different light curve fitters for SNLS. So this is with the SALT-2 light curve fitter. That is then more compatible with Planck. And the SIFTO, which actually dominates the weight in the combined sample, is, again, almost 2 sigma away. So this means if you treat this data as a black box and combine it with Planck, it's going to pull you in the direction of new physics. Okay, so an example is models with arbitrary W, arbitrary equation of state parameter, where the combination of SNLS and Planck will pull you in the region of W less than -1, so into the phantom domain. Okay? So you have to be aware of that. So this is another interesting comparison. So this is using constraints from primordial nuclear synthesis. So the combination of Planck plus high-resolution CMB experiments and WMAP polarization, this is the band of the allowed physical density in baryons, omega b h squared. So that's the band. Then these are the observational limits on helium. There's nothing new from Planck here, because the helium measurements, the errors are so broad. But this is deuterium, and this is more interesting. So the green bands here are the predictions from standard Big Bang nuclear synthesis, with no additional components. Standard value of 3.046 neutrinos. And the width of the band indicates the uncertainty in the theoretical predictions. So for deuterium, this is a compilation of historical measurements of deuterium in damped Lyman alpha and Lyman limit systems. And then this is a very recent measurement of a particularly clean damped Lyman alpha system, which is in extremely good agreement with Big Bang nucleosynthesis. So again, you can use this to infer constraints on the number of relativistic neutrino species, which is completely compatible with the standard value. So here are some results on relevant to inflation. So I'm not going to say a lot about this because Francois is going to talk about this in more detail in the next talk. So for the base cosmology, we get a very 6 sigma deviation of the scalar spectral index from a precise scale invariant value of unity. The new thing is that this is extremely insensitive to the perturbations, the assumptions about the perturbations. So if you add running, if you allow running and tensors, it hardly makes any difference to the constraint. It's also insensitive, relatively insensitive to the matter content. So if you add relativistic particles, additional relativistic species, the favored value is always less than 1. So I think we can be pretty confident that this is actually a real feature of the primordial universe. The scalar spectral index is less than 1. There's no significant evidence for running of the spectral index, so this shows the constraint just with running and then adding tensors. So all compatible with 0. And then this is the tensor scalar ratio at a wave number of 0.002 inverse megaparsecs. And then these are the constraints in the RNS plane for a model without running, and then for a model, parameters with running. And then this is where we expect m squared phi squared to be for different numbers of the E-folds, the inflationary E-folds. And you can see that that's just on the borderline of the 2 sigma boundary of this contour. Of course, you should compare this model with this blue contour because an m squared phi squared model produces negligible running. So those are some of the constraints on inflationary parameters. So our bottom line is that the basic LCDM cosmology with 6 parameters fits the Planck data extremely well. There's no obvious departure from that model. And these are the parameters. Even within Planck, internally, we have some inconsistencies. So this is a measure of the amplitude of the fluctuation spectrum. And this shows constraints in the sigma 8 omega m plane for the basic cosmology derived from Planck cluster counts. So there's a paper that describes the detection of Planck clusters through the SZ effect, and then using those counts to constrain cosmology. The abundances of rich clusters are very sensitive to the amplitude of the fluctuation spectrum. This is the constraint in this diagram that we get from the CMB. And that's at about a 4 sigma discrepancy, okay, which is not understood. So again, either there's new physics, new fundamental physics. For example, you might It's not pretty. It doesn't work very well. But you can try and resolve this discrepancy by adding a 0.3 EV massive neutrino, for example. It doesn't really work, but... so either exotic physics or there's physics involved in clusters that we don't really fully understand. We don't understand how to convert from, SZ measurements through X-ray measurements through to masses of rich clusters of galaxies. But this result has been seen from other analyses of the counts of rich clusters and is another interesting discrepancy. So either it's nonlinear physics that we don't properly understand involving the clusters themselves, or perhaps it's fundamental physics. So we've run a very extended grid of models, large grid of models. The results are all available to you in the Planck Legacy Archive, together with the MCMC chains. So you don't have to repeat this work yourself. You can use that. And what I'm quoting here are values, constraints on extended models for our favored combination, which is Planck plus baryon acoustic oscillation measurements. Okay, as I said, for the base cosmology, these are in very good agreement. And actually, another interesting thing is that they are of comparable power in constraining models. So what we find is a universe that is consistent to sub% precision with spatial flatness, a constraint on neutrino masses of less than 0.23 EV, a number of effective relativistic species that is compatible with the standard value of 3.046. As I said, no evidence of a run. The tensor scalar ratio with Planck, we've now saturated what you can do with temperature measurements alone. The only way that we can improve this number is now to go through to B mode constraints. And then an equation of state for dark energy that is completely compatible with a cosmological constant. So the ultimate boring universe, of which 95% we don't understand. Okay? But here is an example of why I think that I hope I'm not making enemies with the rest of the astrophysics community here. The way that this should be interpreted is that there's a challenge, right? The challenge is to look at the discrepancies between other astrophysical data and Planck and see whether it is actually caused by systematics that are not properly understood, or whether measurements can be improved, or whether you can make a convincing case that those measurements are correct. Because if you can, then we'll be forced into new physics. So this is an example. This is the number of effective relativistic species. This was the constraint I showed you. Planck plus the high resolution CMB experiments combined with BAO, which gives you the blue line. The CMB data gives you the black line. Okay, so that's where the so that's where that constraint that everything is compatible with the standard value of 3.046 neutrinos comes from. But if you believe the Hubble constant measurements, the reset-hour Hubble constant measurements, you get the red line combining with Planck.
But which Hubble, which constant measurement?
That's the Reese value.
So it's not you, really.
I'm sorry?
If
No.
Hubble is yours, then everything is fine.
Absolutely, yeah. So this is now interpreting the reset-hour measurement as absolutely correct. Then you see that you're pulled, now the likelihood for 3 neutrinos is relatively small, and you're pulled in the direction of more neutrino types. But that is coming, that pull is coming from the Hubble constant. It's not coming from the CMB. It's not coming from the Planck data. Okay, so if you treat the other astrophysical measurements as black boxes, then that's the sort of conclusion that you can get. If you add in the BAOs and the Hubble constant, then you get pulled back a little bit, and you find a solution which is now sharing the errors between the experiments. So this solution, if you have 3.5 neutrinos, you can have a solution in which the BAO data, the Hubble constant, and the CMB data are all basically marginally compatible with each other. But you need 3.5 neutrinos to do that. Okay? So now, turning to this, everything is fine with the 6-parameter cosmology at high multipoles from the Planck data. This rainbow diagram shows you the range of values allowed at low multipoles from fitting the full likelihood. And this is not a good fit to the power spectrum at low multipoles. So as the WMAP team noted, there's a funny shape to the spectrum. They tried fitting this with feature models in inflationary potential. But it's not a particularly good fit. Now, there are two aspects to this. The first is that because we have got such good fits to the high multipole part, I think it's absolutely reasonable to focus on remaining anomalies in the data and to see whether we can say anything more about them and find other ways of testing the anomalies, because that's where, in all likelihood, you'll find evidence for new physics. If you just think it's sensationalism, then you should be aware of this in interpreting the results in the Cosmological Parameters paper, because the poor fit here pulls parameters. So you see a number of 2 sigma effects in the Cosmological Parameters paper that are being driven by the poor fit to the low multipoles. If you look carefully at those contours for running of the spectral index, you'll have seen that they were all displaced towards negative running. Not at a statistically significant level, but that is coming almost entirely from the likelihood wanting to fit the low multipoles. Another example in the inflationary paper, if you look at that paper, you'll see that there's 2 sigma evidence for anti-correlated isocurvature perturbations. Again, that's not surprising. What the likelihood is trying to do is to lower the amplitude down at these low multipoles. So you need to be aware of that to interpret these things. So this now just shows you the plus or minus 1 sigma, 2 sigma errors on the ratio of the amplitude that you get from fitting the base model only to multipoles up to a certain value, L max. Okay, so if everything was fine, this would be sitting at unity. Most discrepant point is here, at multipoles of 30. That's a 2.7 sigma discrepancy taken at face value. But of course, there's an a posteriori element in designing a statistic like this. Okay, so we've learned a lot. But as I said at the press conference, we've only analyzed 15.5 months of data. The analysis here for this likelihood and so on was intentionally conservative. We can push the data harder, and we've got more data, and hopefully we'll be able to extract some information on low multiple polarization. So, I think we will be back. Thank you.
Questions? George, I think you already said at the beginning that if you combine the CMB results coming from Planck with other experiments, you don't know how the systematic effects combine, and may drive us to some wrong conclusions.
Yeah, I mean, there's always a risk. There's always a risk that we may develop some sensitivity to systematics in the other CMB experiments. So that's a risk. Well, we have one definite example of that, which, yeah.
Question?
You mentioned how the low L decrease there in power sometimes drives some parameters. I was wondering about the constraints on the tensor to scalar ratio, because the tensors, all they do is add power exactly on this range. So you would think that you are constraining them even more than usual, because even given that the model is low, then you adding more power is even less favored. Is happening, and at what level? Do you know at what level?
Well, we could easily, yeah. I mean, we could easily sort that problem out numerically by looking at the changes. I don't know the number off the top of my head, but of course you know the direction that it would go in. I mean, the data would favour negative tensors.
Next question there.
Yeah, we have seen this morning that the first acoustic peak in the Planck power spectrum is a little bit lower than the one from WMAP. If you would force it to have the same amplitude, in which direction would the cosmological parameters go?
Well, I wouldn't want to do that.
But just as a game?
No, I'm not. I am a scientist. I do not play games. So I'll show you. That is the comparison, okay, between WMAP and Planck. Okay, so the thing is that there is, you know, however you want to interpret it, if you introduce a multiplicative factor, then the points sit on top of each other. And this shows the residuals. And you can see these two experiments are tracking these residuals extremely well. And at these low multipoles, this scatter, the difference, is correlating with frequency, because I can do this. This is showing 100 gigahertz. I can do it for 70 gigahertz, 143, 217. The residuals, they track in amplitude in exactly the way that you would expect from foreground emission. So these experiments are seeing the same thing, apart from a multiplicative scale.
George, I want to ask about tau. In the morning, we saw that tau, if you use WMAP data, but with the dust map from Planck, it goes down to 0.075 or something like this. Furthermore, the EE power spectrum that was shown in the morning doesn't show the jump in the power spectrum at very low L's that would indicate that tau is smaller than. Could you kind of tell us what's...
No, we're not prepared. I mean, at the moment, we're not prepared to use the Planck EE data to, you know, for cosmology. Okay,
that's fair, but your error was a bit...
I'm sorry?
I mean, is the error bars on that tau, you know?
Oh, well, look, as far as the parameters of the basic LCDM model are concerned, it doesn't, you know, we're not particularly sensitive to... We're not particularly sensitive to the WMAP polarization for the parameters of the base model, okay? So, you know, so, yeah, I mean, you know, if you look at the parameters paper, you'll see that in some cases we just truncated the spectrum and did analyses with truncated spectrum. You don't need tau to get the result on the spectral index, for example.
So the last question there. So.
So I agree with your characterization completely that it's up to now the astrophysical community to come back with improved error bars and understand whether something real is being seen. But suppose, for example, there's not new physics in some way that's just the way the universe is, but the direct measurements turn out to be correct. Is there a way that you would see simply to explain the Planck results then?
No, I think you'd need some new physics to reconcile. I mean, if your measurements and errors are right, then I mean, I think we'd need a further improvement in accuracy to just because 2.5 sigma is only 2.5 sigma.
Yeah.
But if we ended up with similar discrepancy at the 4 sigma level, I think you need new physics.
So there are new experiments underway, many groups. This will get better.
Okay, I think, well, just the really last one.
Well, it's actually in relationship to just that question. With the CMB, we measure H, but what is the optimal redshift at which we are trying to draw that? And similarly for these things, and is there a role to be played by playing around with the two epochs?
Sure.
What's the role, George?
Well, I don't know. I mean,
neither do I.
You can have early dark energy, for example.
Okay. Thanks, George. Let's continue with the next talk.